Hey all, Landon here. You may be thinking, wow, are you sick or just sick? I went to the doctor and he said, wow, you look sick. You should go see a doctor. It turns out I've been diagnosed with... Well, I guess there's nothing else I can do than take this cough medicine and talk about the history of the atom, I guess, while all the not sick people are doing whatever not sick people do.
Four numbers spell out the year of the beast. 1800, when English chemist John Dalton looked at this Greek philosopher Democritus' theory of matter being composed of small particles called atoms and said,
"This some serious gourmet shit."
Before his discovery, Dalton made his living as a teacher and was simply doing research in his spare time. But he was about to demonstrate the existence of said atoms that Democritus had only guessed upon. One of his experiments involved investigating the pressure of gases, from which he inferred that gases must consist of tiny particles that are in constant and random motion.
Like ants.
But another experiment Dalton performed was when he researched the property of compounds, substances that consist of more than one element. Dalton showed that a given compound is always comprised of the same elements in the same whole number ratio, and that the different compounds consist of the different elements and ratios. At the end of his experiments, Dalton had concluded that all substances are made of atoms, all atoms of the same element are alike and have the same mass, and that atoms join together to make compounds. But you may be asking me, hey Landon, what did the atom model actually look like? Well... yeah, so one thing I forgot to mention was that since Dalton's theory was that atoms were the single smallest particles of matter, he had envisioned them as solid hard spheres. So the way he modeled them were with wooden balls, which he added holes to in order to have them connect to other atom models with hooks to form model compounds. When Dalton presented his atomic theory, many scientists accepted it almost immediately, and most of it is still accepted today. However, scientists now know atoms are no longer the smallest particles of matter. Which leads us into our next model, so take it away, Ross.
100 years later, in 1900, British mathematician William Thompson, aka Lord Kelvin, proposed the earliest theoretical model of the inner structure of atoms. The model was also supported by Joseph John Thomson, who previously discovered the electron, which is a negatively charged part of every atom, in 1897, though several alternative models were advanced in the earliest 20th century by Kelvin and others. Thomson claimed that the atom held positively charged matter in which electrons are embedded. Joseph John Thomson experimented with the cathode ray tubes in order to show that all atoms contained these electrons. It became known as the plum pudding model because the model had electrons surrounded by a volume of positive charge like negatively charged plums in a positively charged pudding. But it didn't last long, for the model was abandoned in 1911 on both theoretical and experimental grounds in favor of Ernest Rutherford's atomic model. Oh wait a minute, I'm getting ahead of myself.
Thanks, Ross. I'll take it from here. In 1911, Ernest Rutherford and his co-workers Hans Geiger and Ernest Marsden performed experiments that changed the previously accepted model of the atom. The group bombarded very thin sheets of gold foil with fast-moving alpha particles, a type of natural radioactive particle that are positively charged particles with a mass 4 times that of a hydrogen atom. According to the accepted atomic model, in which an atom's mass and charge are uniformly distributed throughout the atom. Rutherford and his co-workers expected that all the atom particles would pass through the gold foil with only a slight deflection, or none at all. Surprisingly, while most were undeflected, about 1 in 8,000 bounced off the gold foil at very large angles. Some even redirected back to the source. With this new discovery, Rutherford explained that it was as if you had fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. Rutherford now needed a new model in order to explain the results. Because the vast majority of atoms pass through the foil, Rutherford concluded that most of the atoms are empty space, or
Nothing!
Anyway, Rutherford also claimed in contrast that the particles that were highly deflective must have experienced a powerful force within the atom. He concluded that the positive charge and majority of mass was concentrated into a small dense space inside the atom, which Rutherford called the nucleus, which his new model called the nuclear model. Rutherford explained that the protons and neutrons, which comprised of nearly all the atom's mass, was located in the center nucleus, while the electrons were distributed around the nucleus and occupied most of the space of the atom. So what happened? Well, Rutherford's model did prove to be a big step towards understanding the atom, but it did not fully address the nature of the electrons and the way in which they occupied the vast space around the nucleus. So if we flash forward to 1915, some more nifty things in the realm of atoms start to occur.
1915 was a big year for science. Alfred Wegener published the theory of Pangea, Pluto was photographed for the first time, Robert Innes discovered Proxima Centauri, and Danish scientist Niels Bohr proposed a new model of the atom following the discovery of hydrogen emission spectra and the photoelectric effect. Bohr made his model because he believed Rutherford's model was inaccurate, so Bohr proposed that electrons do not radiate energy as they orbit the nucleus, but exist in states of constant energy that he called stationary states. This meant that electrons orbit at a fixed distance from the nucleus. Bohr explains that electrons can be moved at different orbits with the addition of energy. When the energy is removed, the electrons return to their ground, emitting a corresponding amount of energy in the form of a photon. This would later become the basics of quantum theory. According to the Bohr model, often referred to as the planetary or solar system model, the electrons encircle the nucleus of the atom in specific allowable paths called orbits. When the electron is one of these orbits, its energy is fixed. In 1922, Bohr was awarded the Nobel Prize in Physics for his work, but like the scientists before him, the model was soon rejected, this time due to Bohr following the laws of classical physics which only applied to large objects. And now that we've covered 4 of these atomic models,
it's time for the moment you've been waiting for.
The year is 1926. Austrian physicist Erwin Schrödinger used the wave-particle duality of the electron to develop and solve the complex mathematical equation that accurately described the behavior of the hydrogen atom. The model comes from the solution to Schrödinger's equation. Quantization of electrons' energies was a requirement in order to solve the equation. This is unlike Bohr's planetary model, in which quantization was simply assumed with no mathematical basis. Remember that in the planetary model, the exact path of the equation was restricted to very well-defined circular orbits around the nucleus. The quantum mechanical model was a great departure from that. Solutions of the Schrödinger wave equation, called wave functions, give at the given point around the nucleus. What Schrödinger proved was that electrons do not travel around the nucleus in simple circular orbits. The location of the electron is what is referred to as the electron cloud. Because of the uncertainty principle, there was no way of knowing where an electron was. In conclusion, Schrödinger is thought of to be the father of quantum mechanics, and his atom model is still accepted today, although many scientists will debate his theory.
So yeah, that's the history of the atom, I guess. And to think that it all started from some philosopher that was ostracized for his thoughts. All of the atom theories have built the backbone of modern physics and helped humanity strive forward. But enough about that, I just got my lab results back. I hope that talking about science for several minutes has done something to it. Oh no. If I don't do anything about this common cold, I'm gonna die in 60 to 70 years!